Let's recall a couple things from last time. We said that the entropy, okay, capital S entropy for our system plus the entropy of our surroundings, okay, this combines to the entropy of the universe, of course, is going to be a maximum when we're at equilibrium. And thus we said that the derivative ds for system plus ds surroundings, this is the change in entropy of the universe, would be equal to what at equilibrium? It's the derivative of a maximum point. It's a slope of 0, okay? So when a system reaches max multiplicity, it's at its max entropy, such that the system is at its equilibrium. And in order to move it away from there and lower multiplicity, I'd have to put in energy to get away from there. Okay? So we can plot multiplicity, okay, versus let n here be the number of outcomes of interest. Okay? And we saw this plot before. It looks something, you know, if we were going from 0 to say 100 heads or whatever it might be, it has a shape that looks something like this. Okay? Where it's centered on 50 if we have equal probability, okay, of our binomial case. And the slope here, and we have a flat 0 slope. So if we let multiplicity be a function of number of outcomes of interest or number of n, then our derivative dw dn will be equal to 0 at the max multiplicity. Derivative equals slope. Okay. So Boltzmann came along and he was like, recognize this and realize that I need this function where the maximum will have a 0 slope because that'll be the most highest maximized entropy. And multiplicity is great, except for it's really hard to work with because it gets really, really big, really, really fast. Okay? So if you plot the natural log of multiplicity, the shape of the curve looks something like this. It still has 0 slope at the point of maximum multiplicity. Okay? Derivative of natural log of multiplicity with respect to n will still be equal to 0 at the maximum. So what we have now is a function that still satisfies the same maximum principle, but natural log of multiplicity is way more manageable numbers. Right? Way more manageable numbers to work with than multiplicity itself. And so from that, Boltzmann wrote his statistical definition of entropy. S is equal to k sub b, this is a lowercase k with a subscript capital B, times the natural log of multiplicity. Kb is Boltzmann's constant. It is equal to gas constant divided by Avogadro's number, or 8.314 joules per mole Kelvin, divided by 6.022 times 10 to the 23rd. The units of Avogadro were what? Things over mole, right? Number of molecules, atoms, whatever. 1 over mole is our units. Okay, so the moles are going to drop out. They're both on the bottom. Yeah. And this is equal to 1.38 times 10 to the negative 23rd joules per Kelvin. Okay. Units are important for entropy. All right. Last time we showed that the units were joules per Kelvin because our definition of entropy was what? What was our classical definition of entropy? Change in entropy delta S was equal to reversible heat flow divided by temp, joules per Kelvin. What's the units of multiplicity? Nothing. It doesn't have any. So what Boltzmann's constant provides for us, this is just a prefactor to make our units pretty. Delta S would be equal to, KB is a constant, Boltzmann's constant, the change in the natural log of multiplicity. So I could have S final minus S initial would be equal to Boltzmann times the natural log of final multiplicity minus the natural log of initial multiplicity. And I know that I can simplify this to the ratio of these two things. Make sure you can manipulate those equations. Page 330 and 331 in your book prove the equivalency of this statistical definition to the classical definition. It's the proof. We won't go through it, but you may be asked to do a problem where you have heat and you have change in entropy and you have to figure out what the change in multiplicity was. You can do that. You have all of that information.